We've established that the angle between the instantaneous net force acting on and the instantaneous displacement of an object, that the angle between those two vectors is of interest to us because the size of the vectors and their relative direction determines at that instant the degree to which the object will be speeding up, slowing down, and or turning. So we would like a way of quantifying like how much these two vectors are supporting one another, how large they are, but also how parallel they are to each other. And so I'm going to propose here in part 3 a mathematical way of doing exactly that, comparing two vectors, A and B, and finding the product of the parallel parts of the vectors, multiplying their parallel parts together, showing how parallel they are to each other, how much they are reinforcing one another. So, okay, in this diagram, I've got two vectors, A and B, and I want to first identify the part of A that is parallel to B. So let's take vector A and break it into components. Make it the hypotenuse of a right triangle with one leg perpendicular to B, call that A perpendicular, and then a leg here parallel to B, call that A parallel. And we see that A parallel, that's the part of A that's parallel to B, the part of A that's working in the same direction as B, that leg right here. So A parallel, the part of A parallel to B, can be found by doing the magnitude of A times cosine of the angle between the two vectors, theta. So A parallel, that is, let's see, this is parallel to vector B. Okay, and the part of B that is parallel to A, I have the same two vectors here, but this time let's break B up into components to find the part of B that's pointing in the same direction as A, the part of B that's reinforcing A. So make B the hypotenuse of a right triangle, and this leg will be B perpendicular, and this leg will be B parallel. And so the part of B that's parallel to A, B parallel, can be found by taking the magnitude of B times cosine theta. So B cos theta, that's the component of B that's parallel to vector A. So if I want the product of the parallel parts, if I want B times the part of A that's parallel to B, or if I want A times the part of B that's parallel to A, that would be A cosine theta times the magnitude of B. This is A cos theta times the magnitude of B. That would be the product of those parallel parts. A cosine theta times the magnitude of B. Or from this point of view, I would take B cosine theta times the magnitude of A. B cos theta times the magnitude of A. That's the product of their parallel parts, and we see that either way, we get the same result. That we can break A into components, or we can break B into components. Either way, we see that the product of the parallel parts of the two vectors is given by the product of their magnitudes times the cosine of the angle between them, since A cos theta B equals B cos theta A. So AB cos theta. This is the sort of thing we've been looking for. The product of the parallel parts of two vectors. A number that characterizes how strongly those two vectors are reinforcing each other. And the product of the parallel parts is known as the dot product because it's indicated by putting vector A and B next to each other with a thick dot in between them, like a dot for multiplying, but thicker than a normal multiplying dot. We're taking some vector A, and we are dotting it. We use dot as a verb here. With another vector, B, A dot B, not A times B, but A dot B. So we have taken these two vectors, and each vector is a collection of three components, x, y, and z components. So we're taking these two vectors, so that's 6 components altogether, ax, ay, az, bx, by, bz. We're taking those 6 components and producing a single number out of them. A single number is just a scalar. And that's why the dot product is also known as the scalar product. It takes two vectors and makes a scalar out of them, these two collections of components, and produces a single value out of them. In other branches of mathematics, it's also known as the inner product. So it goes by all of those names. So the dot product is the product of the parallel parts of the vectors. So we take the magnitude of A, the magnitude of B, multiply them and multiply by the cosine of the angle between them, and that is just a single number, a scalar. Okay. So here we have defined the dot product, a way of characterizing how much two vectors reinforce each other, a single number that tells you how strongly they're reinforcing one another, a single number that represents the product of their parallel parts. So I've got some examples here. Suppose our two vectors are an acceleration vector with magnitude 3 meters per second squared and a velocity vector with magnitude 4 meters per second, and they have some angle between them, theta. Let's find the dot product, A dot V, for the following relative directions. So I've got 5 examples here, and I've already sort of drawn out some vector diagrams and set up our calculation here for these 5 times. First instance, if the angle between them is 0, in other words, if they are parallel to each other, if A is parallel to V, then A dot V, according to our definition of here, is given by the magnitude of A times the magnitude of V. See, we take their magnitudes and multiply them together, then multiply by the angle, the cosine of the angle between them. So 3 meters per second squared is the magnitude of A, 4 meters per second is the magnitude of V, and then we multiply by the cosine of the angle between them. The angle between them is 0 degrees. Cosine of 0 is just 1. So the dot product is 3 times 4, 12. And we take the units and multiply them together. So meters per second squared times meters per second would be meters squared per seconds cubed. And this number would be the dot product of those two vectors, 12 meters squared per seconds cubed. This characterizes how strongly those two vectors are reinforcing or supporting each other. Let's compare that result to some others. What if the angle between them is 60 degrees, some acute angle? So they're partially supporting one another, but not quite parallel. So A dot V will be A V cos theta, so 3 meters per second squared times 4 meters per second times cosine of the angle between them, cos 60 degrees. Okay, cosine of 60 degrees is 0.5, so this comes out to be 6 meters squared per seconds cubed. Half the value that it was when they were parallel to each other. So the same two vectors, same two magnitudes, when they're parallel, the dot product is twice as large as it is when there's a 60-degree angle between them. So you see the reduction in the dot product indicates that they are less supportive of each other with this angle between them. Now, if they're 90 degrees apart, if they're perpendicular to one another, then A dot V is AV cos theta, so 3 meters per second squared times 4 meters per second times cosine 90 degrees, and cosine 90 is 0. The dot product there is 0, indicating to us that perpendicular vectors have no parallel parts. Perpendicular vectors have no parallel parts. The product of their parallel parts is 0. They are not supporting each other whatsoever, but not opposing each other either. So, key result, the dot product of perpendicular vectors is 0. Okay, what if the angle between them is greater than 90 degrees? What if it's a 120-degree angle between them here? They're an obtuse angle, so they're partially opposing one another. Then A dot V is A magnitude times V magnitude times cosine theta. So 3 meters per second squared times 4 meters per second times cosine 120 degrees. Cosine 120 is negative 0.5. That's right, negative 0.5. So this comes out to be negative 6 meters squared per seconds cubed. The negative sign there indicates that they are partially opposing each other. If the dot product is positive, that's telling us that they're supporting one another, or at least partially supporting. If the dot product is 0, they're exactly at a right angle. If dot product is negative, that's telling us that they're partially opposing one another. And then lastly, if they're perfectly anti-parallel, 180 degrees apart, then A dot V is AV cos theta, 3 meters per second squared times 4 meters per second times cosine 180 degrees. Cosine 180 is negative 1, so that comes out to be negative 12 meters per second, meters squared per second cubed. Also negative, indicating they're opposing one another, but more negative than when they were only 120 degrees apart. So they're opposing each other to a greater degree at 180 degrees apart than they were at 120 degrees apart. So there we go. In each of these 5 cases, we've taken these 2 vectors and constructed a single scalar value from those 2 vectors. A single scalar value that tells you something about how large the 2 vectors are and how much they are supporting or opposing one another. Incidentally, what happens if you dot a vector with itself? Like, let's use the velocity from above to find v dot v. So v dot v, nice thick dot there for the dot product. By our definition, that would be the magnitude of v times the magnitude of v times the cosine of the angle between those 2 vectors. But the angle between a vector and itself is 0. A vector is parallel to itself. So times cosine 0. Any vector is parallel to itself. Cosine of 0 is 1. So that's just v magnitude times v magnitude, or the magnitude of v squared. The dot product of a vector with itself gives you the magnitude of that vector squared, which suggests that a way we could express the magnitude of a vector, the magnitude of v, is identical to the dot product of v with itself square rooted. Remember, dot product gives you a single value, so this is just a single scalar value, and if we take the square root of that scalar value, that gives us the magnitude of v.